calculate impedance in a wire, it's important to understand that impedance, represented by Z, comprises both resistance, denoted as R, and inductive reactance, indicated as XL. However, under certain conditions, the inductive reactance of the wire is negligible. In such cases, the impedance can be closely approximated by considering only the resistance. The formula to calculate resistance is R equals ρ times L divided by A, where R represents the resistance in ohms, ρ symbolizes the resistivity of the wire material in ohm meters, L stands for the length of the wire in meters, and signifies the cross-sectional area of the wire in square meters. For copper wire, the resistivity ρ is typically 1.68 times 10 to the power of negative 8 ohm meters. In situations where the wire length is given in feet, it needs to be converted to meters. For instance, 120 feet is equivalent to 36.58 meters. Similarly, if you have multiple wires, such as 3 number 6 wires, you need to calculate the total cross-sectional area. Assuming each number 6 wire has a cross-sectional area of 2.8 times 10 to the power of negative 6 square meters, then the total area for 3 such wires would be 3 times 2.8 times 10 to the power of negative 6 square meters, resulting in 6.24 times 10 to the power of negative 6 square meters. Now let's put these values into the formula. R equals 1.68 times 10 to the power of negative 8 ohm meters multiplied by 36.58 meters, all divided by 6.24 times 10 to the power of negative 6 square meters. When you perform this calculation, you find that the resistance, R, is approximately 0.94 ohms. Therefore, in cases where inductive reactance is negligible, the impedance in the wire can be approximated as 0.94 ohms. Now let's break this down even further. First, the variables that are needed to be defined. Secondly, the source of these variables and their impact in relationship with the impedance. Thirdly, some common mistakes and considerations so a correct calculation can be made. Fourth, how temperature plays a role in impedance and resistance, and finally, a summary. Firstly, let us define the key variables in calculating wire impedance. Resistance, denoted as R and measured in ohms, quantifies the opposition a wire offers to the flow of electric current. It is a fundamental property that depends on the material, length, and cross-sectional area of the wire. Resistivity, symbolized by the Greek letter ρ and measured in ohm meters, is an intrinsic property of the wire material. It indicates how strongly the material resists electric current. Copper, for example, has a low resistivity, making it an excellent conductor. Length, represented by L and measured in meters, is the distance the electric current travels through the wire. A longer wire naturally offers more resistance than a shorter one of the same material and cross-sectional area. Cross-sectional area, denoted as and measured in square meters, is the area of the wire's cross-section perpendicular to the direction of current flow. A larger cross-sectional area allows more current to flow, reducing resistance. Inductive reactance, symbolized as XL and measured in ohms, arises from the inductance of the wire. It opposes changes in current flow and becomes significant at higher frequencies. Impedance, denoted as the measured in ohms, is the total opposition a wire offers to the flow of alternating current, AC. It combines both resistance and inductive reactance. In many low-frequency applications, inductive reactance is negligible, and impedance is primarily determined by resistance. Secondly, let's explore the sources of these variables and their relationship with impedance. The resistivity, ρ, is a material property obtained from reference tables. Different materials have different resistivities. Copper and aluminum are commonly used in electrical wiring due to their low resistivities. The length L is determined by the physical layout of the electrical circuit. Longer distances between components increase the wire length and thus the resistance. The cross-sectional area, A, is selected based on the current carrying capacity required for the circuit. Larger wires with greater cross-sectional areas can handle higher currents without overheating. The relationship between these variables and impedance is defined by the formula R equals ρ times L divided by A. This equation shows that resistance, and consequently impedance when inductive reactance is negligible, is directly proportional to resistivity in length and inversely proportional to cross-sectional area. Inductive reactance, XL, depends on the frequency of the AC signal and the inductance of the wire. At low frequencies, XL is often negligible, simplifying the impedance calculation to just the resistance. Thirdly, it's crucial to avoid common mistakes and consider important factors for accurate impedance calculations. Ensure consistent units. Convert all measurements to meters and square meters before plugging them into the formula. Use the correct resistivity value for the wire material. Refer to reliable reference tables for accurate values. Account for temperature effects. Resistivity changes with temperature. Use temperature correction factors for precise calculations, especially in extreme environments. Consider skin effect at high frequencies. The current tends to flow near the surface of the wire, reducing the effect of cross-sectional area and increasing resistance. For multiple wires in parallel, calculate the equivalent cross-sectional area by summing the areas of individual wires. This reduces the overall resistance. Be mindful of wire gauge and ampacity. Select the appropriate wire gauge based on the circuit's current requirements to prevent overheating and voltage drop. Fourth, temperature plays a significant role in impedance and resistance calculations. The resistivity of a material is temperature dependent. As temperature increases, the atoms in the material vibrate more, hindering the flow of electrons and increasing resistivity. To account for temperature effects, use temperature correction factors. These factors adjust the resistivity value based on the operating temperature of the wire. The temperature coefficient of resistance, TCR, indicates how much the resistance changes per degree Celsius or Fahrenheit. Use the TCR to calculate the resistance at different temperatures. In high-temperature environments, such as industrial settings or enclosed spaces, temperature effects become more pronounced. Use appropriate temperature-rated wires and consider ventilation to mitigate temperature-related issues. Failing to account for temperature effects can lead to inaccurate impedance calculations and potentially unsafe operating conditions. Finally, to summarize, calculating wire impedance involves considering resistance and inductive reactance. In many low-frequency applications, impedance can be approximated by resistance alone, using the formula R equals ρ times L divided by A. Ensure consistent units. Use the correct resistivity value. Account for temperature effects. Consider skin effect at high frequencies, and be mindful of wire gauge and ampacity. By following these guidelines, you can accurately calculate wire impedance and ensure the safe and efficient operation of electrical circuits. Furthermore, let's elaborate on inductive reactance and its impact on impedance at higher frequencies. Inductive reactance, XL, is the opposition to the flow of alternating current, AC, caused by the inductance of a wire or circuit. It is measured in ohms and depends on the frequency of the AC signal and the inductance of the circuit. The formula for inductive reactance is XL equals 2 times pi times F times L, where F is the frequency in Hertz and L is the inductance in Henries. Inductance arises from the magnetic field created by the current flowing through the wire. When the current changes, the magnetic field also changes, inducing a voltage that opposes the change in current. This opposition is inductive reactance. At low frequencies, the inductive reactance is small and often negligible. However, as the frequency increases, the inductive reactance becomes more significant and can significantly affect the impedance of the circuit. In high-frequency circuits, such as radio frequency RF circuits, inductive reactance dominates the impedance. The impedance becomes primarily inductive, and the resistance is often negligible. In such cases, the impedance is approximately equal to the inductive reactance. To minimize inductive reactance, use shorter wires and keep the conductors close together. This reduces the inductance of the circuit and minimizes the impact of inductive reactance. Shielded cables and twisted pairs are also used to reduce inductance and minimize inductive reactance in high-frequency circuits. In summary, Inductive reactance is an important factor to consider when calculating impedance in AC circuits, especially at higher frequencies. It opposes changes in current flow and depends on the frequency and inductance of the circuit. By understanding inductive reactance and its impact on impedance, you can design and analyze electrical circuits more effectively. Let's talk about the cross-sectional area of different wire gauges and how to select the appropriate wire size for a given current carrying capacity. Wire gauge refers to the standard sizing system used to describe the diameter of electrical wires. The American wire gauge, AWG, is the most common standard used in North America. The AWG number is inversely proportional to the wire diameter. A smaller AWG number indicates a larger wire diameter, and vice versa. For example, a 12 AWG wire is larger than a 14 AWG wire. The cross-sectional area of a wire is related to its diameter by the formula it equals pi times r squared, whereas the area and r is the radius of the wire. The radius is half of the diameter. The cross-sectional area determines the current carrying capacity of the wire. A larger cross-sectional area allows more current to flow without overheating the wire. The National Electrical Code, NEC, provides guidelines for the ampacity, or current carrying capacity, of different wire gauges. The ampacity depends on the wire material, insulation type, and installation conditions. For example, a 12 AWG copper wire with THHN insulation has an ampacity of 20 amps in typical residential wiring. To select the appropriate wire size for a given current, consult the NEC tables and choose a wire gauge with an ampacity that meets or exceeds the required current. It is always better to choose a larger wire gauge than a smaller one to provide a safety margin and reduce voltage drop. Voltage drop is the reduction in voltage along the length of the wire due to the resistance of the wire. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, use larger wire gauges and keep the wire runs as short as possible. In summary, wire gauge, cross-sectional area, and ampacity are important factors to consider when selecting the appropriate wire size for an electrical circuit. Consult the NEC tables and choose a wire gauge with an ampacity that meets or exceeds the required current. Use larger wire gauges and keep the wire runs as short as possible to minimize voltage drop. Let's also discuss different types of wire insulation and their temperature ratings. Wire insulation is the non-conductive material that surrounds the metal conductor of a wire. It provides electrical insulation and protects the wire from damage. Different types of wire insulation have different properties such as temperature rating, moisture resistance, and chemical resistance. Common types of wire insulation include thermoplastic high heat resistant nylon coated THHN, thermoplastic heat resistant THW, thermoplastic underground feed OFF, and cross-linked polyethylene XLPE. THHN insulation is a common type of insulation used in residential and commercial wiring. It has a temperature rating of 90 degrees Celsius in dry locations and is resistant to moisture and oil. THW insulation is similar to THHN but has a lower temperature rating of 75 degrees Celsius in wet locations. UF insulation is designed for underground use and is resistant to moisture and chemicals. XLPE insulation has a high temperature rating of 90 degrees Celsius in both wet and dry locations and is commonly used in high voltage applications. The temperature rating of the wire insulation indicates the maximum temperature at which the wire can operate safely. Exceeding the temperature rating can cause the insulation to break down, leading to short circuits and fires. When selecting wire for an electrical circuit, choose a wire with an insulation type and temperature rating that is appropriate for the application and environment. Consider the ambient temperature, the operating temperature of the equipment, and any potential exposure to moisture or chemicals. In summary, wire insulation provides electrical insulation and protects the wire from damage. Different types of wire insulation have different properties such as temperature rating, moisture resistance, and chemical resistance. Choose a wire with an insulation type and temperature rating that is appropriate for the application and environment. Okay, let's also explore the concept of impedance matching and its importance in electrical circuits, particularly in high-frequency applications. Impedance matching is the process of making the impedance of a load equal to the impedance of the source. The load is the device or circuit that receives the electrical power, and the source is the device or circuit that supplies the power. When the impedance of the load is equal to the impedance of the source, maximum power is transferred from the source to the load. This is known as impedance matching. Impedance mismatch occurs when the impedance of the load is not equal to the impedance of the source. In this case, some of the power is reflected back from the load to the source, reducing the power delivered to the load. Impedance matching is particularly important in high-frequency applications such as radio frequency RF circuits, where even small impedance mismatches can cause significant power loss. To achieve impedance matching, various techniques can be used, such as using impedance matching networks, transformers, or stubs. Impedance matching networks are circuits designed to transform the impedance of the load to match the impedance of the source. Transformers can be used to step up or step down the impedance to achieve impedance matching. Stubs are short lengths of transmission lines used to cancel out the reactive component of the impedance. In summary, impedance matching is the process of making the impedance of a load equal to the impedance of the source to maximize power transfer. Impedance mismatch can cause power loss, particularly in high-frequency applications. Various techniques can be used to achieve impedance matching, such as using impedance matching networks, transformers, or stubs. Now let us consider how the wire material and its purity affect the resistivity and, consequently, the impedance. The material of the wire plays a crucial role in determining its resistivity. Copper and aluminum are the most commonly used materials for electrical wires due to their low resistivities. Silver has even lower resistivity than copper, but it is more expensive and less practical for most applications. The purity of the wire material also affects its resistivity. Impurities in the material can increase the resistivity and reduce the conductivity of the wire. For example, even small amounts of impurities in copper can significantly increase its resistivity. High-purity copper is often used in critical applications where low resistance is essential. The manufacturing process also affects the purity and uniformity of the wire material. Proper manufacturing techniques can minimize impurities and ensure a consistent cross-sectional area, resulting in lower and more predictable resistance. In summary, the wire material and its purity are important factors to consider when calculating impedance. Copper and aluminum are commonly used due to their low resistivities, and high-purity materials are preferred for critical applications. Also, how to measure wire resistance using a multimeter and how to verify impedance calculations. Measuring wire resistance using a multimeter is a simple and effective way to verify impedance calculations. A multimeter is an electronic instrument that can measure voltage, current, and resistance. To measure the resistance of a wire, follow these steps. Firstly, ensure that the wire is disconnected from any power source. Secondly, set the multimeter to the resistance measurement mode. Thirdly, connect the multimeter leads to the ends of the wire. Fourthly, read the resistance value from the multimeter display. When measuring low resistances, such as the resistance of a short length of wire, it is important to account for the resistance of the multimeter leads. This can be done by shorting the leads together and noting the resistance reading. Then subtract this reading from the measured resistance of the wire to obtain the true resistance. To verify impedance calculations, compare the measured resistance value with the calculated resistance value. If the measured and calculated values are close, then the impedance calculation is likely accurate. If there is a significant difference between the measured and calculated values, then there may be an error in the calculation or a problem with the wire. Possible problems with the wire include corrosion, damage, or excessive length. In summary, measuring wire resistance using a multimeter is a simple and effective way to verify impedance calculations. Compare the measured resistance value with the calculated resistance value to ensure accuracy. Furthermore, let's delve into the concept of skin effect and its impact on impedance at high frequencies. Skin effect is the tendency of alternating current, AC, to flow near the surface of a conductor at high frequencies. This phenomenon occurs because of the self-inductance of the conductor. The changing magnetic field produced by the AC current induces eddy currents within the conductor. These eddy currents oppose the flow of current in the center of the conductor, forcing the current to flow near the surface. The depth to which the current penetrates the conductor is called the skin depth. The skin depth decreases as the frequency increases. At high frequencies, the skin depth can be very small, meaning that the current is concentrated in a thin layer near the surface of the conductor. The skin effect increases the effective resistance of the conductor at high frequencies. This is because the current is flowing through a smaller cross-sectional area, increasing the current density and the resistance. To minimize the skin effect, use conductors with a large surface area, such as hollow conductors or conductors made of multiple strands of thin wires. These conductors provide a larger surface area for the current to flow through, reducing the current density and the resistance. In summary, skin effect is the tendency of AC current to flow near the surface of a conductor at high frequencies. It increases the effective resistance of the conductor and can be minimized by using conductors with a large surface area.